Okay, calculus, we're moving on to 6.6. And what we want to make sure that we do is we understand that the derivative of an amount means the rate at which the amount is changing. So if we have an example where we have R of t is represented by the amount of water measured in cubic feet in a swimming pool, this is giving you context measured in hours, then R prime of t would represent the rate at which the amount of water is changing. So just so we're clear as far as looking at the units, so as we do the derivative of R, that equals R prime of t, then what that means is that the units for R prime of t would be in cubic feet per hour as you examine all of the units. Maybe I can highlight for you cubic feet per hour. Whereas if we have the work backwards, so to speak, so going backwards, the antiderivative, or the integral from a to b of the rate, is equal to the amount of change. So just to give you context of the same example above, I'm just going to go to the answer key. Oops, I'm too far down. And you can see he wrote out per instead of how I wrote it as a fraction. But anyway, here's your answer, and it represents the amount of water that has drained from the pool between the time of t equals a to t equals b hours. So I think it might be, let's stop right there. I'll just go to the example. Where if we are given this problem and we're trying to find the midpoint Riemann sum, I guess it's kind of unfair because they didn't give you enough directions here. But if we did the midpoint from 0 to 10, 10 to 20, then 20 to 30, so we have 3 rectangles. Each width is 10, but if we're doing a midpoint, we want the y value at t equals halfway between 0 and 10, which is t equals 5. Times 1.6 plus the next width from 10 to 20 is 10 times the y value at 15, and then the next width is still 10 times the y value of 1.6. Now it's up to you how you would answer this, but 10 times that just moves the decimal over once. So I don't know how you would add that together, but you'd have 32 plus 31, so that'd be 63. Now, if we're working backwards, remember it's the amount, we're taking away that rate. So I guess this is just velocity of a particle, so it's just moving 63 feet. Let me go back. I think I went too fast, so you might want to hit pause if you didn't get this written out. I just want to make sure that we had the context of the question as we had it. So this represents the total change in distance from t equals 0 to t equals 30. So think of net distance, because we don't know unless they tell us that it's strictly increasing, even though it's really not, because it stops at t equals 0 at that value. So that gives you the context of that question. So as I move on to the next one, just think of it this way, as the integral from 5 to 25 of a of t dt is going to represent b of 25 minus b of 5. So as we look at b of 25 is 1.6 and b of 5 is 1.6. So this is going to give us 1.6 minus 1.6, or 0, because we are finding the average acceleration is another way of saying this. We're looking at the feet per minute. So just to give you some context, I want to make sure that I'm giving you the right context that we have here. It represents the amount of change in velocity from t equals 5 to t equals 25. minutes. So again, feel free to pause the video as we move on to the next portion. So what we can do in the next problem, we're getting into some more AP word problems, some free response practice, more or less. And notice that the directions even give you the clue that we have a twice differentiable function, so we can go both ways, derivatives, antiderivatives. And notice that the units that they give you, T is in minutes, and W is in degrees Fahrenheit. So yeah, I think that's helpful. So using the data in the table, estimate W prime of 12. Well, if we're not given 12, it makes sense then to use numbers on either side, and I would be able to approximate W prime of 12 as doing a difference quotient of doing W of 15 minus W of, whoops, I meant to write 9. I almost wrote down the Y value. All over 15 minus 9. So just a little bit of work. I don't know if this would be a calculator, no calculator problem, but you could probably do this in your head. Nine minus 8 is 1, 7 minus 1 is 6. And as far as units go, since we're doing the rate of this, it makes sense to say degrees Fahrenheit per minute. And because we're estimating W prime of 12, that is the instantaneous rate. So again, I'm just trying to confirm exactly how they would write it. So at T equals 12 minutes, the temperature of the water in the tub is increasing at a rate of apparently 1.017 degrees Fahrenheit per minute. So as we move forward to the next problem, just think about what this means. Is if we want the integral from 0 to 20 of W prime of T dt, basically what that's saying is asking you to do W of 20 minus W of 0. So in our problem, 71 minus W of 0 was 55. If you can do that in your head, 71 minus 10 would be 61, minus 6 would give me there, so I'm looking at 16. This is just degrees Fahrenheit. So this is just the amount changed over that time span from T equals 0 minutes to T equals 20 minutes. That's what that value represents. But again, just to give you the confirmed, what it represents is the amount that temperature rose, is one way you can say it, from T equals 0 to T equals 20 minutes. So now what we can do is we can actually switch over to a calculator type problem for the next problem. So, and they'll do this to you. Let me switch back to our notes. Is they'll give you a table of values, and then you stop taking a table of values at 20, and then they came up with an equation for the next 5 minutes. And that equation was given to you as a rate. And so based on this model was the temperature of the water at time T equals 25. Well, let's think of it this way, is this is an accumulation problem where you can do W of 20, that's your initial condition, plus the integral from 20 to 25 of W prime of T dt will get me to W of 25. So we've been doing this type of problem, so notice how some of the things I've been mentioning before are still happening, that these numbers have to match up in the right order, to get us there. So why did I say this is a calculator-based problem? And I wish I could see it all on one screen, but anyway, we're going to start with the 71, W of 20, and then we're going to use our calculator for this part to get us what our final answer is. It's just an accumulation problem. So as I pull up the calculator, I'm just going to slide this down so I can see both out 0.4 second square root of x, cosine of 0.06 x. You might want to double check that you typed it incorrectly. 0.4 square root of x cosine 0.06 x. And you might want to double check that you're in the right mode. We need to be in radians. So as I go back to my problem, so I have 71 plus math. The integral is the ninth option down from 20 to 25 of alpha trace y1 in terms of x. And according to that integral, or that rate, it increased another 2.043 degrees. Now, actually, I probably wouldn't have even written this stuff. I probably would just go straight to that answer, that 73 point, I already forgot what it was, 043 degrees Fahrenheit is W of 25. So again, I'm going to go to the calculator just to confirm that's exactly what they have. You don't have to give context in this sense anymore. And this might make a little bit more sense written out this way opposed to the way I like to write it. So that is up to you. I think I'm going to stop the video because I have 2 more problems and I'm not going to rush through this. So I'll see you in the next video.